Thank you so much for that kind introduction. Again, my name is Romero, Talamás. And today, I'm going to talk about fusion energy and really sources of energy and how we can make them better for our planet. It turns out we use enormous amounts of energy in our planet. And unfortunately, most of those sources of energy are carbon-producing sources, meaning they produce carbon dioxide, they produce greenhouse gases, and only 20% of those sources are non-carbon emitting or non-greenhouse gas emitting sources. As you've heard today, it is urgent to decarbonize our economy, our infrastructure, because we are harming the planet, because we're running towards a climate disaster, and so we have to do it as soon as possible. We need all options on the table to be able to decarbonize our economy to get to the so-called net zero, meaning net zero carbon emissions overall. There is hope. We are heading in the right direction. And the charts that you see here in green is the readiness of technologies that are already on the market that the Energy Information Administration estimates we need to get to a net zero scenario by 2050. But in light blue are the technologies that are still being developed, that we need to develop before we get there. As you can see, just in the last 2 years, we've made tremendous progress, but we have still a lot of work to do. So enter fusion energy. Fusion energy is considered the ultimate source of energy because the fuel for it is abundant. The fuel actually is non-radioactive. Yes, it is a form of nuclear energy, but it's not radioactive. It's everywhere on Earth's crust, so you wouldn't have to defend or fight wars for the resources. It's incredibly energy dense. In the plot behind me, it's actually, it's an imperfect plot. It's actually inaccurate because at the very top of the plot, it depicts train loads of coal, but 2 million tons of coal will be equivalent to the same energy that you could get for 1.3 million tons of oil and also about equivalent to about 30 tons of uranium oxide, the uranium ore that you need to refine and to get fission energy, which is the type of nuclear energy that we have today. But only about 0.6 tons of deuterium. And deuterium comes from water, actually. It's an isotope of hydrogen, so it's just a little bit heavier hydrogen, and it's found naturally on water. It's also very difficult with fusion energy to use it for nefarious purposes. It's very easy to monitor compared to fission energy. And the waste that comes out normally from the power plant is not radioactive. Just to give you an example, a 1,000 megawatt power plant, so a power plant that will be enough for a fairly large metropolis, will use 8,000 metric tons of coal every day, but will produce 30,000 tons of CO2, 600 tons of sulfur oxides, the stuff that gives you acid rain, and about 80 tons of nitrous oxides. All of those are byproducts that are harmful to the environment and or to us. In comparison, for fusion energy, you will need about 0.5 kilogram of deuterium, again, you can get from water anywhere, and about 1.5 kilograms of lithium, and lithium, the same stuff you have in the batteries of your phones, for 1,000 megawatts. In comparison, if you want a sense of scale, for the state of Maryland, about 6 million people, you only about 4 times that. That fuel you can fit in a small suitcase, or if you want for the whole year, in a truck. And compare that to, of course, thousands of train cars of coal, with the only byproduct every day for the example of the 1,000 megawatt power plant will be less than 2 kilograms of helium, which is not a greenhouse gas, and if anything, we need more of it. Now, you say, well, why are we not doing this? And We are investigating how to get there, how to do it safely. It turns out it's not trivial, it's not easy to do fusion energy. Fusion is the inverse of what we have today, fission energy. Fission is splitting the atoms. Fusion is bringing them together, and you have to get them really, really close. You have to get the nuclei of those atoms together very, very close before they fuse, and in the process release enormous amounts of energy. There's several ways of doing that. Gravity is one. The sun works on fusion energy, but we cannot manipulate gravity on Earth, at least to the level required to get a reactor going. Then there's inertia. You can put the fuel in a little capsule, blast it from all sides, compress it very fast before it disassembles itself, get to the thermonuclear condition, and then you have energy. But the problem is, engineering-wise, is very challenging. There's still huge practical problems that need to be solved to get there with inertial confinement. Then it turns out you can also use magnetic fields. Why? Because for fusion energy to happen, to get the atoms so close together, you need to overcome the electrostatic repulsion of the nuclei, the protons, plus and plus, repel each other. And because you have to get it so close, one way to do it is to slam the particles against each other. Now, you want to have a reactor, right? So you wouldn't do it one particle at a time or one pair of particles at a time. You have to do it many, many particles at a time. So you need, the recipe for fusion is really enough particles colliding head-on per unit time. So they have to be at high enough temperature. So many particles colliding at head-on, it gives you high temperature. And because most of the collisions are scattering collisions, not head-on collisions, you need to keep enough number of particles for long enough there, and that's called the confinement time. So that's a triple product: density, temperature, and confinement time. It turns out temperature has to be about 100 million degrees. So that's about 10 times hotter than the center of the sun. At those temperatures, the atoms lose their electrons. You have a soup of charged particles. And it turns out that you can keep those charged particles using magnetic fields. So in essence, you can make a magnetic bottle. So what we're investigating is magnetic confinement. Now, the main concept is called a tokamak, which is a donut-like chamber that uses a lot of electromagnets, the short way around and the long way around the torus, to confine the plasma. It is the most advanced concept, and it's the one that you will likely hear achieve the important milestone of getting more energy out than you put in. There's another concept that is even more stable called the stellarator, and has coils that are twisted. They look like potato chips. You need a lot of them, and you need to have them very precisely placed. Now, this is fantastic, and I hope they get there soon. The problem is, once they get there, to translate that from the laboratory to a commercial reactor is going to be very, very challenging. Because imagine what happens when you have to fix something inside the chamber. You have to disassemble the whole thing to get there and reassemble it. That's downtime, that's time lost and materials, etc., that you have to account for. Now, what we're working on at UMBC in collaboration with our colleagues at College Park is a concept called the centrifugal mirror. It's also a magnetic confinement concept, but it's much simpler in the sense that it's just a linear machine, which you're seeing here behind me in the screen. In that case, imagine if it breaks down, you can easily remove the chamber by just sliding it out, or removing one of the magnets, repairing it, putting another one in, etc. The machine is also more compact. It relies on rotating the plasma supersonically to be able to stabilize it, meaning so you don't lose all the energy you're investing to get to the thermonuclear condition. It is estimated to be cost competitive, and it's steady state, versus if you remember the inertial confinement, you will have to shoot lasers to compress this little capsule. Well, we wouldn't have to do that. Now, where are we? So we are already getting data. The density that we're getting is now reactor relevant. And the other quantity, confinement time, we measure it. So it turns out when we rotate the plasma, you store some energy there. We stop providing energy, and then we see how long it takes for the energy to come out of the configuration. And we measure that as the momentum confinement time. And we're getting very encouraging results, very fantastic results. In fact, to me, this is one of the best plots. I know it's not for you, but to me, it feels amazing. And we're on our way to measure temperature, and this is informing our models on translating to a reactor size, which will be a machine not much bigger than what you see in the next picture. So please stay tuned for more results because we're going to get there pretty soon. Thank you.